And I'm really happy to get the invitation to talk on one of my research projects. I just completed this project last year. The technical content of this project has already been done last August, and we are in the implementation phase right now. So as part of the implementation work, we are working with, especially with Harris County Flood Control District, which is very they have different properties, channels, and slopes, and my research aligns with their, property management. And also, we are trying to reach out to TxDOT and other DOTs to expand our research results. And some of the government entities, they are going to adopt few part of our research output in their future investigation and also design methodology. So thank you so much again, Dr. Ferez, for introducing myself. I will not take time to introduce myself again. So my presentation outline will be, first I will go over the introduction of the research we just completed and the objectives, what we did for this particular project, and what are the methodologies we used, and the results and discussions, and finally the conclusion. So first of all, if we look at these two figures here, these two are the highway embankments. Now, first of all, let me ask to the audience. So you all have driven through 290, I-10, or any other highways in Houston or some other areas, right? Everybody? For sure. So this is the slope, and this is the frontage road, and there's the highway. So we can see some kind of cracks, right? And this is a failed slope. Now, apparently, it seems like this is a very shallow slope failure, but this is an indication that the slope is going to fail tremendously if it is not taken care of immediately. So that's a sign. So it causes, it happens because of the soiling and shrinkage characteristics of clay soil. And let me inform you that most of the highway embankments and slopes we have in Texas, 95% of them are constituted with clay soil, high expansive clay soil, and they have a very good potential for soiling and shrinkage because of the fluctuation in the environmental conditions. Now, when I say environmental conditions, the main two parameters are precipitation and temperature. So let me explain the things, what is the mechanism for the shrinkage and soiling. So just after the construction of the slope, I'm just assuming, let's say this slope was constructed back in 2000, just for example. Now, during the construction procedure, definitely the DOTs, the TxDOT, and whatever regions we have the slope in, they maintain proper compliance, and they constructed it following all the manuals. Now, just after construction, everything is good, but we cannot actually control the environmental parameters. We cannot stop the precipitation. We cannot say that, okay, the temperature should not be more than 70 degrees Fahrenheit. We cannot control that. That's not in our control. So what happens with time, this clay soil, because of this fluctuation, so if there is a small amount of rainfall, they will try to infiltrate through the slope soil, and in the shallow depth, when I say shallow depth, maybe typically it's 1 feet to 2 feet, that soil will be kind of get affected. Affected means the soil infiltration, and the water will need some space within the clay soil. Now, one of the property of the clay soil is as soon as it receives any water, then it tries to expand, especially for the expansive soil. Now, if it expands, that means this soil will need more room to accommodate that water, right? So what happens, even if we see these cracks on the pavement or on the shoulder of the road, but the initiation actually occurred 2 feet or 3 feet below the ground surface. So what happened, the soil actually started to move a little bit, and that crack started to form. Now, if this crack is not taken care of immediately, this crack width will increase significantly, and at certain point, there will be a catastrophic failure. And if it fails, then we won't have, and during that time, any vehicle, moving through this, they could have in a dangerous accident or something. So, do you see any kind of, a black, asphalt patching here? Do you see that? Now, that's basically, this was done because I particularly know about this site. So this asphalt patching was done in 2008 or 2009. And after the patching, the crack started to propagate from this side. So we cannot stop it because of the clay soil's property, expansive soil. This crack will form, and they need to, TxDOT, they need to repair this slope time to time, every 6 months or every 4 months sometimes. And now let me give you an information. TxDOT, they spend almost 100 to 200 million dollars every year just to repair existing slopes, just to repair these small repairs. No new construction, no new building, just to repair these slopes. And there are more than 4,000 different types of slope in entire Texas. 4,000, it's a lot. And they are taking care of all the 4,000 slopes. And these repair works, then they spend on an average 100 to 200 million dollars based on the severity of the environmental condition. So again, this is one indication of the slope failure, and this is a shallow slope failure. So if it is not taken care of immediately, it's an indication there will be a catastrophic failure if soon. So basically, based on the literature and from the geotechnical perspective, the environmental factors, especially the temperature and the rainfall, those are the two main factors that causing problems to these slopes, highway embankments in Texas. So again, as you see that billions of dollars property damage and almost 25 to 50 casualties are reported annually in the US due to slope failure. Now, this is information or this statistics from US Department of Transportation. There's overall US, and in Texas, the number is approximately 5 to 10 out of this 25 to 50. Now, erratic climatic loading and problematic soil, those are the two conditions. Now, if you have problematic soils there, and on top of that, if you have the fluctuations in the environmental condition, these two together make the slope soil in a worse condition, and that makes the failure of the slope. And that's why TxDOT and any other DOTs who have this expansive soil, they are having tough time to maintaining these slopes. Okay, so highway embankment slope failure occurs due to different reasons. Now, one of it is the geological conditions. Now, if we go to California or western part of US, we will hardly see any expansive clay soil there. Most of the soil type we have there is sandy type, sandy silt. So they don't have much clay soil. So what happens, even if they have a erratic climatic patterns, they don't have this kind of problem that we saw in the previous slide because their soil type is different. Now, geologic condition is a factor. Now, hydrological influence, and definitely the precipitation, the rainfall, and other environmental factors, they cause a tremendous problems to the slope soils based on whatever soil, the subsoil we have for that particular soil. And of course, the topographical features, the weathering process, soil plant activities, and the climatic conditions. Now, for this particular region in Texas, the climatic condition is the major factor that causes the slope to fail, and that causes TxDOT to make repetitive repair actions for different slopes within Texas. Now again, the slope failure, the mechanism is cyclic changes in moisture content and soil suction. Now soil suction is the negative pore water pressure. Now the soil suction or the negative pore water pressure, that actually adds additional strength to the soil. Now if we have added strength, that's good for the slope. Now when it rains, the rainwater actually destroys that negative pore water pressure within the soil, and that causes reduction in the soil strength properties. Now, typically, we do triaxial test using the collected soil to determine the strength parameters, and we have specific, strength parameters C and Phi that we call C and Phi. Now, that negative pore water pressure, there's an added, strength, to that slope soil. But the rainfall that causes, reduction in that negative pore water pressure, eventually reduction in the strength. Now, ultimately, is the cyclic changes in the moisture content induce recurring soiling and shrinkage. Now, if we look at this, just after any rainfall event, let's say there is a dry, period, especially in Texas, we have almost more than 90, 95, or 100 degree Fahrenheit during the summertime. Now, the soil started to shrink and this crack occurs. Now, after the summer, let's say there is a minimal amount of rainfall. Now what happens, these cracks are an easy path of rainwater to go deeper into the slope. Now initially, if there is no crack, maybe the water infiltration will be maybe 1 feet to 2 feet. But as the cracks are there, this time, these cracks will allow the water to go deeper into the slope, and the deeper layer of the soil will have been extreme effect because of this crack. So what will happen, the deeper layer of the soil, they started to get affected, and their unsaturated condition of the soil, they started to decrease, and eventually there is a heavy potential for a catastrophic failure if the rainfall intensity and the duration is high. I will talk about the rainfall index that we have for the entire Harris County. And this is called actually the desiccation crack. Desiccation crack. And once the water enters through the cracks, there is a huge amount of hydrostatic pressure. Now, the soil is actually taking its own load, right? The soil has its self-weight, and also whatever traffic or the vehicles is passing through the lanes, the soil or the slope is carrying that loads. Now, if there is an easy path of water, the water will generate hydrostatic pressure, and the soil will have to carry that hydrostatic pressure as well. But maybe during the design, we didn't consider that hydrostatic pressure. So that cracks will add additional implied stress into that soil layer. So this is the overall problems with the highway embankments in Texas. So in this project, we tried to see what is the impact of the rainfall in the greater Houston region, and how they can affect the slopes and the channels we have within the Harris County by investigating the rainfall duration and intensities. So for that, our main objective was to examine the rainfall intensity and duration for the last 20 years in Harris County. Now, this project was, I was the PI, and two other faculties from the University of Texas at San Antonio, they were the co-PI, and we together developed this, intensity duration curve. And then we try to incorporate that IDF into our numerical modeling to see the effect of this rainfall pattern for slopes instability. And we developed a rainfall pattern based on the high resolution radar data and conduct a numerical analysis to evaluate the effect of precipitation on the slope's stability. So that was the overall objective of this project. And definitely when we do any numerical modeling, there are several types of parameters that need to be incorporated in the model. So when we do the slope stability analysis, we need the rainfall data. We need the slope in the soil data. So basically the slope is a soil material, right? So we need to see what are the strength properties of the soil and what are the physical properties of the soil. So to come up with, as we determine the rainfall pattern for the greater Harris County, we collected several samples within Harris County from different depths. And a few of the industry partners, they helped us to collect samples, and we did all the laboratory characterization in our PV lab. So as you can see that, this is an indication that we have a problematic soil in Harris County. Now, any soil within this A line and U line, they are high to low plasticity clay soil. Especially if you see any soil above liquid limit of 50, those are having extreme expansive characteristics of soil, and those are creating the problems for this. Now, these soils are also problematic, but not like this soil here. So we see that most of the soils are within the high to low plasticity, clay region, based on the soil samples we have collected from the greater Harris County region. And also, these are the engineering terms. Minus 200 sieve means what are the percent passing number 200 sieve, or what are the fine contents. So when from engineering perspective, we say fine content, that's basically the silt and the clay portion of the soil. And we see that most of the soils, we have some other soils, but most of the soils are more than 50%. And they have, at different depths, from the shallow surface to almost 25 feet depth, we have, a greater number of fine contents in the soil. So that's an indication, and we needed this information to incorporate in this numerical model to simulate the effect of the rainfall. Now, to investigate the rainfall pattern, we actually used a rain gauge, almost more than 100 rain gauges within the Harris County, and University of Texas, San Antonio, the professor from there, he helped us to gather all the data and statistically analyze the IDF. And the multi-sensor precipitation estimate MP and the combination of the radar data were observed to develop the rainfall pattern. And we have a spatial resolution of 4 kilometer by 4 kilometer. And we also use the multi-radar, multi-sensors product integrate data from the multiple radars and radar networks. Now, most of this work was conducted by University of Texas at San Antonio, and they gave us the raw data, and then we incorporated those into the IDF and then into the numerical simulation to see the effect of this rainfall. Now, these are the location, the red dots, these are the location of the rain gauge that we analyzed for this study. And you see there are actually not more than 100, actually more than 150 rain gauges we have within the Harris County. And this is the results we have gathered. This is the, the results, very, simple, analysis here. So if we look at this, this is Harris County, and this is Montgomery County, and this is Galveston County, this is Fort Bend County, this is Brazoria County, I believe, and this is another county, I forgot the name. So if we look at this, if we look at the contour here, so annual average rainfall almost 1,700 in this part and in the eastern part of Harris County, as you can see from this graph. So the Montgomery County and Brazoria County and also the Fort Bend County, they don't have much effect like the rainfall we have in the greater Harris County. So this is the annual average based on the data we have gathered from all the more than 150 rain gauges we studied in the Harris County. And this is again the annual rainfall from year 2000. As I said, we investigated the last 20 years rainfall, and this is the annual rainfall from year 2000 to 2021. And we see this line here. This is the rainfall from the year 2017. And I believe we all know what happened in 2017. Anybody remembered? 2017, what is it remembered for? For the Hurricane Harvey, right? So Hurricane Harvey. So I will show you more data what happened Hurricane Harvey. So we see that this is a kind of maximum. Now this data is almost 1,700 millimeter rainfall. Now to add that, we saw that out of that 1,700 millimeter rainfall in 2017, almost 1,200 millimeter rainfall occurred just in the month of August 2017 when the Hurricane Harvey occurred. And month of August, but actually it's the 7 to 8 days duration, because Hurricane Harvey occurred from August 22 or 23 until September the 1st or September 2nd. And this is the monthly precipitation. As you can see, the the average is 5 to 10 millimeter and sometimes 15 millimeter rainfall per month. But you see 2017, this is the month of August, we had almost 35 inch of rainfall, which is equivalent to, if we multiply with 25.4 in millimeter unit, it's a tremendous amount of rainfall that occurred. And during that time, a lot of slopes within Harris County and also in Montgomery County, in Brazoria County, lot of failure occurred in the slopes we have in these counties. Some of them were very catastrophic failure. Now, this is the accumulated precipitation. If we see that for the last 20 years, in January, we had almost 2,000 millimeter of rainfall. And we see that every year, July and August, we have the maximum rainfall. We have the maximum rainfall in the month of July and August. Now, why did you do that? We actually had this analysis to see what happens to the slope stability or the slopes condition during the month of August and September. And we saw that based on a lot of reports from TxDOT and USDOT, the most of the slope failure occurred in the month of July, August, and September. And when we try to compare the results, we see, yes, in the August and September, there is maximum rainfall also in July. And these are the 3 months when TxDOT has the toughest time to repair all the slopes. And they have the maximum number of failures during this time, which is July, August, and September, every year during this time. Now, this is the IDF developed by our team, and this is the the IDF data we incorporated in the numerical simulation in the GeoStudio package to investigate what will be the pattern of the slopes instability based on this. So if you look at this, we have a 1 year to almost 1,000 years IDF curve. Now, if you look at this, just I'm giving one example. So in the x-axis we have the storm duration, and in the y-axis we have the precipitation intensity. Now, if we look at the data for 1 year return period, so what will happen if there is a continuous 10-hour rainfall, and we go to this curve and we see the precipitation intensity almost maybe 6 to 7 millimeter per hour. And this precipitation intensity requires to get input into the software, and that will tell us if there is a rainfall for 10 hours with an intensity of 6 to 7 millimeter per hour, what will happen to the slope. That we investigated first through the seepage analysis, and then we transform the seepage analysis to the slope stability analysis and to see what's going on. So again, we have 1 year return period data, 2 year, 5 year, 10 year, and up to 1,000 years. Now, typically for most of the design in Texas and any other states in US, 100-year return period rainfall data is used for the design, for most of the designs in Harris County and all over the US. But we have investigated what will happen to 1 year, 2 year, 5 year, up to 100 years. But most of the cases, 100-year return period data is mostly used. Now, as we have the rainfall intensity data and the storm duration, then we try to incorporate all this information into the GeoStudio package. Now it has, it has a couple of packages. Now, first of all, it has TempW. Now, if you look at this, we have SIPW, SlopeW. It has more packages. TempW, which can account for the temperature variation. Now, temperature variation was not a major factor in our study, so we didn't use that. So we used SIPW to see how the water will seeping through the soil. And once it seeps through the soil, what will be the strength? I mean, what is the stability of the slope using the SlopeW module? So this geometry of the slope is one of the slopes in Harris County, and it is in the eastern part, somewhere near Pasadena or somewhere. We use that geometry to see what's going on. So we use the SIPW and import SIPW output to SlopeW, and that gave us the strength parameters. I mean the stability of the slopes. Now, once we add the rainfall intensity, now we used the rainfall intensity I 3.07. That means 3 millimeter per hour rainfall, and it was a 2-year return period. We just checked it, and also after 2 days of continuous rainfall. So first of all, if we look at that, so this is before the rainfall condition. We have the slope soil strength parameters, and this is the water pressure. This is the water pressure. And this is after we incorporate the rainfall, I 3.07 millimeter per hour. So what is the pore water pressure? So first of all, before we go to the slope stability analysis, we need to see how the pore water pressure has changed significantly. Now, before the rainfall, let's see this water pressure is negative 2200 to almost 2000 PSF. Now, negative means it's the negative pore water pressure or the soil suction. And as I said, that's good for the slope. That add additional strength to the soil, right? Now, after we input the rainfall data, we see that the pore water pressure reduced to almost 55 to 50 KSF if we look at this contour. And at the top of the slope, this is almost like a red, and in the red we have almost 0 to 5 PSI of PSF of negative pore water pressure. That means that 3 millimeter per hour of rainfall that will cause a significant change in the negative pore water pressure of the soil. That's an indication. Even if we don't do the slope stability analysis, we see that that's an indication that the negative pore water pressure is reducing significantly, and it is about to cause a major failure in the slope. Okay, so before I explain this graph, I want to show you. So the stability of slope is measured through the factor of safety. So the factor of safety is basically in my term, I say it friend over enemy. Friend over enemy means if your friend is higher than the enemy, that means your factor of safety is high. That means if your factor of safety is 1, that means your friend is equal to enemy, right? Friend is equal to enemy. Now, your friend is trying to save the slope, and your enemy is trying to fail the slope. So friend over enemy means friend is the shear strength of the soil, and the enemy is the applied stress or the reduction in the strength. So because of the reduction in the slope soil, so your enemy is, what is happening? Your enemy is increasing. So factor of safety 1 means your slope is at the verge of failing, right? And if your slope factor of safety is less than 1, that means your slope has already failed. And if your slope is more than 1, that means your slope is stable. Now, if the factor of safety is 2, it is stable. It is 3, it is stable. Now, should we make our factor of safety 2, 3, 4, 5? That's the question that is, a burning question to all the DOTs and everybody. Now, typically, if we want to make the factor of safety 2 or more than 2, that means your slope must be in a kind of flat. We cannot make any steeper slope. Now, when I say steeper slope, it means if our slope is steeper, we need a lot of space in the right of way, right? If our slope is steep, that means we are cut down the slope ratio. That means the slope is allowing us to have more frontage lengths, if you understand, right? So is steeper the slope, bad it's bad for the stability, right? But sometimes we have to make, and TxDOT, they are kind of forced to make, steeper slope to accommodate more frontage lanes, because based on the traffic study, they found that for this particular section, a lot of traffic has been added based on the traffic study. So they have to add 1 or 2 additional lanes. So they cut the slope, make the slope steeper, and within the cutting zone, they add additional lanes, maybe 1 lane or 2 lanes. And as soon as you make the slope steeper, that makes your slope more vulnerable to failure. Okay. So if we look at this, first of all, if we look at the first graph here, which is your rainfall intensity 1.14 millimeter per hour, and if it continues for 7 days. Now look at that. Initially, before the rainfall, when there was no rainfall, 0 day, this your x-axis is the time in days. When there is no rainfall, your initial factor of safety was almost 1.8, right? Almost 1 point or 1.7 something. Now, as we started the rainfall in the simulation, we see that as time is going down, your factor of safety is reducing linearly, right? It's reducing, it's reducing, it's reducing. Now, if we look at this data is for 7 days. 7 days, so 3 days, so 6. This is 6 days, so 7 days. Somewhere here, we stop the rainfall. We see that the factor of safety is almost near to 1. That means if this rainfall continues for 7 days, this intensity is not that much. 1.14 millimeter per hour still is kind of less. But if it continues for 7 days, your factor of safety could have been to almost near 1, and that can cause severe failure to your slope. Now, if we look at this, the last one, which is I equal to 5.31, that means the rainfall intensity is high, and if it continues for 1 day, the last one, we see that even if it is, if we compare the slope of this and slope of this, it's reducing abruptly, and it comes to at least almost to 1 factor of safety within 1 or 1.5 days, something like that. That means this 1 day rainfall with this intensity can cause significant factor of safety reduction within a short period of time. So that's an indication. And so we stop the rainfall after 1 day, and you see that the factor of safety is not like that. It will go back to its original condition. It kind of stays, and it's increasing very slowly. You see that this is not kind of flat. It is increasing, but at a very slow rate. Now, let's say after 15 days, again, there is a rainfall. There is a potential that from this point, it will start to drop again. It depends on how much time we are giving this slope for healing, right? So again, similarly for I equal to 1.78 for 4 days, for 2.24 for 3 days, for different duration and different intensities, we try to see for each of the cases, the slope from the initial condition, the factor of safety reduces significantly. And if this, just for example, if your 1.14 millimeter per hour of rainfall, it continues for 8 days, we will say that maybe it will continue like this. And as I said, if the factor of safety less than 1, that means the slope has already been failed. Now, when I say failed, it means it's not the entire slope failed. Now, this will cause the shallow slope failure. Shallow slope failure. That means the top 2 to 3 feet will be affected. Now, if we don't repair the slope, again, if there is any rainfall event like this, the next 2 to 3 feet, that means from the surface, 5 to 6 feet of the soil, they will fail. And if we don't repair that, again, it will be gradual. And if we keep that slope as it is, then at certain point, it will be a catastrophic failure. And to repair that, TxDOT or any other DOTs, they will have to spend maybe a couple of $1 million to repair that. But the problem is that will create a tremendous amount of casualties, as I show you the statistics there. Now, if you look at this, so this is the output from the model. We see that initially the factor of safety was almost a 1.85 because the input of the rainfall, as you see. As soon as we put the rainfall, you see the factor of safety is 1.19. So these red dots from the model, it indicates the factor of safety. So you see that after the rainfall, which is I equal to 3.707 millimeter per hour for two continuous days, we see that the factor of safety reduced significantly. And we model this for each of the cases, and based on that, we develop this curve to see, from this curve, we can find out what's going on and what will happen. It's a kind of prediction. Again, so this is the effect of geometry. Now, as I said, we can make the slope steeper, we can make the slope flat, right? If we make the slope flat, we will lose space from the frontage spaces, right? Or the right of way. And the same soil profile, the soil condition, the strength parameters, everything was identical. We just changed the slope soil. Initially, it was like this. Right now, it is like this. So we make a steeper slope. And we see that the initial condition, the factor of safety is 1.588, which was previously 1.856 before we input the rainfall. Now, once we put the rainfall data, we see that the factor of safety is 0.722. That means with this rainfall, if the slope is steeper, in that case, this rainfall will cause the slope fade, and it will be a shallow slope failure. So this is an indication that, this rainfall can cause significant problem, and it is causing significant problem to the TxDOT and other DOTs where they have expansive soil. And and if we make it even steeper, I will say without the rainfall, the slope stability will be less than 1.2 or 1.1 something. Now, typically industry practice, federal rule, state rule, county rule, your factor of safety should be at least 1.5, at least. And if it is more than 1.5, that's very good. But if it is less than 1.5, then it's not accepted. We need to do something to make sure that based on the numerical simulation or the numerical model, our factor of safety becomes at least 1.5. Now, as I said, if it is 2, 3, 4, that's even good. But to make the factor of safety more than 2, sometimes you have to make your slope a ways flat, and you cannot have enough space for the right of way and the frontage roads. So even if we want more factor of safety, but we cannot do that. Right? Now, based on all these results and analysis, and I have shown just a couple of results from our research, because there is a this kind of graphs I have more than hundreds. I don't want to show everything; it will take a lot of time. And based on the research we did, and we shared the results with Harris County Flood Control District, the geotechnical division. And they are kind of they will adopt few of the methodology or the system that we have developed for their future, their channels management and everything. So we saw that the subsoil condition of the study area widely varies, and we got different types of soil, but mostly CL and CH, which is high plasticity to low plasticity clay soil. That was one of the factors. And the hourly rainfall intensities were observed to be significantly variable for different return periods from the IDF. And we saw that high intensity and low duration, or low intensity, high duration, that both the cases cause significant problem to the slope. It depends on how long it will take for the slope to get to the factor of safety of 1 or close to 1. And with a higher hydraulic conductivity of the slope soil plays a significant role in the precipitation. Now, higher hydraulic, we actually didn't do any hydraulic conductivity test in this research. It takes a lot of time to determine the hydraulic conductivity, but we use some correlation to determine if this is the soil, then what is the typical hydraulic conductivity of the soil. And we were kind of conservative in assuming that data, because that data must be kind of precise when you do the actual design. So if we see that the results it's a kind of very significant with the conservative data. Now, when we do the actual lab test and we have the actual data, we incorporate that, and that will be higher than the conservative data for sure. That will be even more catastrophic. So we saw that the rainfall intensity is low to high duration for different duration period, and they cause significant problem to the slopes, and that causes slope to fail. Initially, it starts the shallow slope failure, and then if it is not repaired immediately, it will go to the deeper layer, and eventually there will be a catastrophic slope failure. And that causes TxDOT to spend millions of dollars to repair all these slopes. That's all from me. Thank you so much.
Thank you, Dr. Jubair, and we'll open the floor for questions and answers. I think an important thing on here one, it goes to soil physics based on is the mineralogy of the clay.
Yeah.
You have The one layer, the multi-layer, you have like kaolinite, which basically it's a monolayer clay that doesn't shrink very, very slowly.
Right,
Small shrinkage.
right,
But if you have the memorionite, which
Exactly.
basically shrinks and swells a lot.
exactly, right.
So if you know that you're gonna use a shrinking and swelling clay
Mhm.
and it's gonna fail,
Mhm.
why using it?
Okay, it's a very good question. So if we know that the clay property or the clay soil we have in our project area that contains significant amount of montmorillonite or illite or kaolinite, which is the clay mineral that causes the problem to swell and shrink. But if we want to reduce all this soil and bring new soil, the transportation cost of the new soil and removing all this, it will be more than 50% of the total project cost. So even if we don't want, but we cannot do it, that the cost is very, very high, transporting the new soil and remove all this problematic soil. That's, you cannot do it.
But I think one thing that you mentioned, especially about the hydroconductivity,
Mhm.
okay. The hydroconductivity of the clay depends on its soil moisture content.
Yeah.
So if you allow the clay to dry out,
Mhm.
will be cracks.
Right.
So the hydroconductivity will be higher.
Right.
So one thing that they have been doing in buildings to protect buildings from shrinking and swelling is you maintain the moisture content around the building
Right.
at a level that doesn't allow it to dry. So
Right,
you
right.
minimize that. So that when the rain comes, when
Right.
the high intensity
Right.
rain comes,
Mhm.
your hydroconductivity will be low.
Right.
So your stability, the stability of your slope will be
Mhm.
better.
Right. Right.
So if you cannot, use a non-shrinking, non-swelling
Mhm.
clay, what you can do is make sure to irrigate that area
Right. 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 It's
to
a,
maintain soil moisture so that when that big rainfall event comes,
Right.
Your soil is more prone or more stable than if you didn't irrigate it. Or you
Right,
didn't
right, right.
maintain it.
So this concept is applied to all the households and the neighborhood we have. There is a kind of moisture barrier concept or soil improvement, which is called. So the top 3 to 4 feet, which is most vulnerable to the change in the environmental fluctuation. So we put some kind of moisture barrier and can be a geosynthetic material or lime stabilization. So what lime does, when it gets mixed with the soil, it reduces the plasticity characteristics of the soil. So even if it rains, the soiling characteristics of the soil that reduces significantly and it will not soil. But if it soils, the lightweight structure, which is our house, it's a 1-story or 2-story house, that house will have floor cracking and you will see the wall cracking there. But for it is applied to the pavement. If we look at the pavements, TxDOT apply a lot of lime stabilization and other treatment method for the top 4 to 5 feet of the soil so that it doesn't have the soiling or the shrinkage properties. It reduces down. But for the slope is sometimes 1 mile to 2 miles big, sometimes big. So stabilizing that long slope is sometimes very, very costly. So sometimes they keep it as it is and they just do repair, repetitive repair actions. That's it.
Well, the reason of mentioning this, there is a room for research that
Exactly.
can
Right.
help.
Right.
Basically optimizing the stability.
Right,
of
right,
the
right. To
slope.
add that, there's a question. Yeah, I can take the question.
So, yes, you have a question here? Oh, you have a question? Go ahead.
Thank you for your presentation. It's clear. And I have a couple of questions.
Sure.
That you already did the technical part, right? And you're still going to apply.
In the implementation phase.
Yes, the implementation phase. So are you going to implement in the real field or are you going to use a simulator in the lab?
So no, not in the lab. It will be implemented by the government entities and also the industry partners. For example, how they will adopt this method. Now, we have the rainfall data and we saw how it is affecting the highway embankment, right? Now, some of the industry partners, especially the Harris County Flood Control District, they are closely monitoring the results and also looking at the output from this research. Actually, they have channels. They don't have highway embankments. The highway embankments and all the slopes are maintained by TxDOT. And all the channels and the detention basins are managed by Harris County Flood Control District. Now, when I say channel, this is also a slope, right? and it consists of different types of soil, mainly the clay soil. Now they want to cut down their repair cost. Now whatever channels they have, as they know that this rainfall is causing problem, they're trying to use some kind of barrier. Now to make sure, they are first looking at these results, and accordingly they will implement, okay, to repair or to make sure that our channels are long lasting. We need to do that because these research results are saying that this intensity of rainfall is causing problems to the highway embankments, so as the channels. So they are investigating the results right now, and they will eventually implement new method to make sure that their channels are properly managed. They don't have catastrophic failure, something like that. Not in the lab, because this entire numerical modeling, we have only the laboratory characteristics of the soil from the lab, and everything else was from the numerical simulation and the data collection from the existing rain gauges we have within Harris County.
And maybe a follow-up. We can see that there is different slopes along the way when we drive. So right. So is there like particular optimum slope for different soil categories?
Yes, typically, if typically TxDOT maintain a 1:3 slope at max. If it is 1:4, then that's good. But because of lack of proper spaces, sometimes they have to go with 1:2.25. It means if we go one vertical, you go 3 horizontal. So you see that if it's a 1:1 slope, that means 1 horizontal, 1 vertical. It's a steep slope, and they cannot do it. It's not recommended by the federal rules and also the state and other counties. It's not recommended. Even if you see that numerically, you put high strength parameter, the soil is very good. The soil based on the numerical simulation is more than 1.5, but it's not allowed at all. So, sometimes, it's typically 1:3, but sometimes 1:2.25 or 1:2.5 based on, we need space for the frontage area. So we need to cut the slope and make the slope steeper.
Yes.
It's high. Oh. So one quick question. Are there any studies out there where they use a filler, like a plastic material or a thermoplastic or a thermoset to do the sealing of those cracks?
Very good question. Now, to seal the cracks, they typically use asphalt patching, as I said before. Now, TxDOT is also applying a different moisture barrier. So if I will show you this figure.
I think it's sharing the screen, but go ahead and,
Okay. So if we look at this, what TxDOT is trying to do, the main source path of moisture movement into the slope is through the, edge of the slope, right? Edge of the slope. So they are putting a barrier-like things, which is, which extends from here up to a depth, almost 5 to 6 feet here. So if we can reduce the movement of water through this moisture barrier, then most of the water from the rainfall, they will be kind of go as a runoff, and they will accumulate at the toe of the slope. Now they put a high capacity drainage system there, so that no moisture accumulation occurs at the edge of the slope, and it doesn't create this kind of cracks. Now typically they use this kind of asphalt patching, typically. Now with more and more vulnerability because of the environmental condition, this patching is not enough nowadays. They are trying to use different methodology. Now, one of the things that I have been investigating for the last 2 years, but that's not in slope, that's for the landfill application, which is the engineered turf. Now, turf is a composite, geosynthetic material with synthetic turf and geocomposite and synthetic material. So I tried to see if we put any synthetic or the engineered turf materials over the soil, and I have also a control section where there is no engineered turf, and I compared the results. The turf are actually, retaining the moisture retention, moisture equilibrium. Moisture equilibrium means, there is no significant gain in moisture or loss of moisture because of the environmental fluctuations. But for the control section, I saw that there is no turf. The fluctuation of the moisture is significant. So I will also share that result with TxDOT and Harris County Flood Control District, that engineered turf is, kind of maintaining the moisture equilibrium. So you can use that as a barrier here. and eventually you will have significant, cost reduction for the repair. Turf is a composite material, so it's basically a synthetic grass-like thing. It's not the actual grass, and below the synthetic grass, we have a geomembrane. Now, a geomembrane is 100% impermeable synthetic material, which is widely used as the bottom liner for landfill. It's a polymer material, right? It depends. There's a lot of different types of materials. Yeah.
I think this is a good area of research we have been doing, and Anoop can talk to you or Atikur about the use of biochar.
Biochar, yes.
We have been doing some work
Mhm.
measuring infiltration and also soil water release curve that you showed there. So we are active in this area very well, and we have been we have a couple of publications on using MRMS across Harris County and
Okay.
gauge comparison of gauge, rain
Okay,
gauge and also MPE also.
Okay.
So this is one area where maybe we should talk.
Sure. I just want
about
to add, there is one professor in UIUC. His name is Krishna Reddy. He is doing a lot of research on the biochar material. He's from University of Illinois, I believe.
Yeah, we have been doing this work, and I think we can share with the results of that with you.
Sure.
We have some online questions. Dr. Ripendra Awal, he's asking, did you consider pavement and previous area and the road surface when you simulate seepage? Based on the pore pressure figures you showed, it seems you did not consider this. Can you elaborate?
For the pavement, no, we didn't consider that. We specifically considered the soil strength parameters, and based on the strength parameters, whatever input we have in the numerical simulation, it automatically generated the pore water pressure. We specifically didn't consider that, but I have, my existing research sites, they have the tensiometers and the moisture content sensors, moisture sensors. Now these plots are, giving me the time-dependent change in the negative pore water pressure and also the soil moisture, and that I am trying to simulate those and incorporate those in the slope.
Okay, one more question. As you can see in Highway 290, the trees and the road embankment, do you think these trees will help reduce slope failure?
Yes, technically the tree actually helps to, to retain the strength of the slope, or, it makes the slope stable. But, if the tree is big enough, if it is grass root, that's good. But if it is tree root, that's sometimes not good. That, during the evapotranspiration process, the tree roots, they take most of the water, and they will cause, shrinkage. I don't know. They will cause easy shrinkage to the slope. So sometimes grass is good. I mean, grass is always good, but tree root is, I don't know. Okay, yeah. So the question is if tree and other types of grass are good for the slope to make it or to retain the strength of the slope. As I said, the grass root is very good, but the tree root is not good specifically for the slope, because the tree root will extract, a lot of water, and they will cause, faster, for a very rapid shrinkage of the soil, and that will cause another problem. So grass root is good, not the tree roots.
Okay, I think this is a good discussion. I guess we can follow up further with more discussion. Any other question before we close?
Thank you for the presentation. Does this study include other forms of precipitation like snow, sleet, and drizzle? Because these forms of precipitation may matter, rate of infiltration and the rate of surface runoff.
Right. It's a very good question. Yeah. The snowfall or sleeting is not a major problem in Texas, but I can assure that, in the coming next 10 to 15 years, as we see that during the month of February, January, for the last couple of years, we have some kind of snow and sleeting problems. And typically, Texas is not ready for snow right? You see there is a snow, we close our universities, we close all the business, right? But if you go to New York, Montana, Minnesota, the snowfall and everything is very common. So even if there's a significant snowing, they don't close their businesses, and their DOTs are ready to take care of the snows. But TxDOT is not, because this is not very uncommon in Texas. But there is a room for incorporating the effect of snow and sleeting problem in the numerical simulation to see what will be the effect in terms of those.
Well, thank you. I'd like to, before we close, we have our Associate Dean, Executive Associate Dean for Research. He has to present a couple of slides. So is it ready? He's joining us, Dr. Memoli, through Zoom, right? He's gonna present the slides, right, for Dr. Memoli? Ah, it's displayed? Okay, so we'll display and we'll read through it. Oh. So this is a good discussion, and I guess it's most of it is soil physics and soil erosion.
Right.
And we have been doing lots of work in this area. So I think it's.
And I want to add, this is the Department of Agriculture. I have a project with Dr. Ram Ray with at NASA, and one of the projects I'm doing, my NSF grant, Dr. Ray is giving some of his area to use that land for my research. So I'm grateful to the Department of Agriculture and Human Science.
Well, we need more collaboration. So
Yeah,
that's
sure,
good
sure, sure.
to see that. Okay, I think it says International Collaboration Seminar, opportunity with Bogor Agriculture University, IPB, presented by a delegate from this institute. Okay, so it's going to be on Kark Seminar Room, Friday, this Friday, tomorrow at 2 p.m. So tomorrow at 2 p.m., there will be a seminar in Kark Seminar Room by this group from international, from Bogor Agriculture University from Indonesia. So all are invited to interact, listen to the seminar, and at the same time, interact with our visitors. So you are all invited and encouraged to be there. With that,
Thank you
let's
so
thank our
much.
presenters today, and thank you also for your attendance. Give him another round of applause.